Okay, let's deal with the knotty problem of serial dilution. I've left my aseptic technique stuff over here because we're going to use aseptic technique throughout, so we need to remember those things. So why do we use serial dilution? Well, when we're taking samples from, the environment, you're taking it from a cream cake or a burger van or the school canteen, sample of seawater, sample of tap water, sample of river water. Probably you've got about 11 billion bacteria in there, and you'll have lots. And so in order to be able to see which ones are alive, which are the ones that you're most interested in, the dead bacteria are neither here nor there, you will need to dilute that sample first. So here is our sample that we want to do a count of, and you will probably have done this with milk or Yakult or some other thing full of bacteria. What's the other one? What's the other one called? The Yakulty thing. Help me. No, she's not listening. Those little yogurty drinks, you know what I mean. So you want your sample there, and it can be in whatever. This one's just showing it in a little glass flask. And the idea is that we want to spread those bacteria out. We want to dilute them so that when we plate those bacteria out, they are more spread out. So we can see here, if we've got lots of them, they're all together and we can't count them. And, if you dilute them a bit further, we might be able to count some of them, and dilute them further, we've got clear, distinct colonies. Dilute them a bit further, we've got even less colonies, less, and finally zero. So this is the point of serial dilution. It's just to spread your bacteria further out in your broth so that when you plate them out, then they're countable. And so what we're interested in here is our live bacteria. So this is a technique to count live cells that can reproduce to form a colony. And we're assuming here that each one bacteria that lands on the plate gives rise to one colony. Now, that isn't always the case, and we'll talk about that later. So here, what we're saying is we've got 2 colonies on there. That means that 2 bacteria in that 1 ml that we've transferred and spread out on the plate, there's 2 live bacteria. Each one of those has reproduced to give lots of bacteria and make a visible colony. So we can say with confidence, okay, we've got 2 bacteria per milliliter in there. So that's the whole sort of principle. Now obviously, in terms of questioning and testing your mathematical skills, they might ask you to calculate the dilutions that you are dealing with. So if I just draw a little test tube, and the whole point is you're diluting into either broth or distilled water, but it's whatever you're doing it into, it's got to be sterile. So here you've got sterile broth. It would be my preferred option. You might have a buffer solution in there. It might be distilled water. And in this example, we've got 9 ml of broth or buffer in there, and you're going to put into that, it's a nice contrasting colour, like orange, you're going to put into that 1 ml of your sample. So these are our undiluted bacteria. This is our sample, and we've got 1 ml of those. And obviously a ml and a centimetre cubed are the same thing, so let's not get confused. Now that means that overall we've got 10 ml in there, of which one of them is sample. So we've got a 1 in 10 dilution. Now if you're doing a tenfold dilution, the idea is then, once you've mixed those together, You'd then aseptically transfer them. You do all the flaming the neck of the bottle thing, using a clean syringe, sterile syringe, so your equipment's sterile, and you transfer a mil into another 9 mils, so you're diluting it by 1 in 10 again. Notice that all you need to do, this is a maths trick, is add on a 0 at the bottom. If you're more confident using the standard form, you can then use, this is 1 over 10 to the 2, 10 to the 3, 4, 5, 6. If you then convert it into per, then it's per -1, -2, -3, etc. You might not get those numbers. So one of the ways in which examiners like to know that you're reading their carefully crafted questions, and why wouldn't they, is that they might give you something like 9.9 and 0.1. And you might be thinking, well, how in the world would I work that out? Well, you've still got 10 mils altogether. You add those two together, and our top value, that means 0.1 in 10. Now you need to know how many 0.1s can I fit into 10, so you have to turn it upside down. 10 divided by 0.1 will give you 1 over 100. The same would apply if you've got, if you're diluting and you've got, it doesn't really matter what numbers you've got, but another common one is to give you 99 and 1. So again, looking at 100 here altogether, and you've got 1. Now obviously if you're doing 1 out of 100 dilutions, these numbers along here will change because you're going to have to add 2 zeros on each time. So you get 1 in 100. Once you do it again, you've got 100th of a 100th. So your next one would be 1 in 100, 2 more zeros. 1 in 100, 2 more zeros, 2 more zeros. So that's a very fast way, isn't it? Because we're going down from a 100th to a 1000th to a millionth in sort of 3 steps. Whereas this, it takes us 1, 2, 3, 4, 5, 6 transfers to get down to a millionth. So it depends probably how many bacteria you feel you've got in your sample in the first place. So once you've done all that aseptic sterile transfer and you've mixed them all up so they're nice and evenly dispersed, the next stage is to get them to produce these colonies, and we can do that by transferring them onto a sterile agar plate. So you need 1 for each dilution. Generally, and certainly when we did it, we would probably have only done 2 dilutions per team, because otherwise it's a heck of a lot of equipment. But were you doing this at university, for example, or as part of your job as a microbiologist, you would be plating out all of them. And the idea is to choose a plate that gives you a reliable number. So you don't want to use one that's only got 2 or 0 colonies on, because although they're dead easy to count, you want to increase the reliability. So even 17, dead easy to count, but you're generally looking at sort of, 100 to 300 bacteria on your plate. They're only tiny. And you dot them and you've got a little clicker counter. So you would choose one with a reliable number, clear, countable colonies. So if we look at our other ones, these ones are not reliable, the numbers are too small, and these have got too many colonies to count, and some of the colonies are sort of overlapping like that, so you can't actually tell where one colony starts and another one ends. So we need clear countable colonies with no overlaps. Now nevertheless, that might still give us an underestimate, because it may be that one of these colonies, it's 2 bacteria that have kind of landed side by side but just produced 1 colony. So you might get an underestimate even so. So just to have a look at the results, kind of results you would get. So this is a really lovely picture of the internet. I love the internet. This is the results of an account. This is a 1 in 10 dilution series. So this one here is a 10th diluted, and you can see that the bacteria pretty much cover the plate. We've got a few gaps appearing in the 1 in 100. We've got some more gaps appearing in the 1 in 1000. This one would be 1 in 10,000 then. Another 0 on. This one's probably got too few to count, so 1 in 100,000. And then this one's definitely, once we get to 1 in a million, there's hardly any on that. We've only got 2 colonies. So we can count these, nice clear countable colonies, but there's too few to be reliable. Much better to count this plate, even though we can see that some of these colonies are really quite close together. When you're calculating back up then, so let me just do, this plate here, because I've got some colonies that I can actually physically see and count. I'm not going to count that, there's too many. Let's pretend this one's reliable. So, I'm going to count them. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 colonies. My dilution is 1 in 100,000. So I need to multiply by 100,000. 100,000. All I need to do is add some zeros on now. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, because I put my commas in, which I think is really good practice, I can see that that's 2.4 million, which looks slightly better than a big long string of zeros stretching off into the middle distance. You do need to also watch out for little odd things because of the reading the question thing again, that sometimes at the top they will say, well, they've plated out 1/2 ml or 0.1 of a mil. If they've done it by 1/2 ml, you'll need to double your number. If it's 0.1, you'll need to multiply by another 10. They're just things to watch out for. What can I say? Read the question, read the question, read the question, read it properly.